Hello, I'm Roshan Gupte, and today with me are my fellow classmates from MEC 2, Rashmi Joshi and Prerana Umbarkar. Today, as part of our research-based learning activity for numerical methods and computer programming course, we will be discussing a research paper in the mechanical systems and signal processing realm. Our task was to summarize the paper and, most importantly, identify and elaborate on the numerical method used to carry out the procedure. So here goes. The paper we selected dealt with the development of multiple linear regression-based models for the fatigue life evaluation of automotive coil springs, published by Elsevier. The design of automobile suspension systems is an extremely time and cost-intensive process. One important aspect is finding the fatigue life of an automotive coil spring based on the vertical vibrations of the vehicle and natural frequencies of the vehicle's suspension system. However, computing fatigue life of automotive springs using strain measurements in physical testing procedures can be complex. This served as the motivation for carrying out this analysis. This paper essentially elaborates how to predict the fatigue life of the automobile coil spring using MLR, which is multiple linear regression, a numerical method. The models were later validated by comparing the fatigue life values predicted by the models and with those predicted from strain measurements. The results showed a good agreement between the predicted and experimental values.
What is MLR? Multiple regression is just an extension of simple linear regression. In simple linear regression, we have one-to-one relationship. So to explain the variation or to make predictions about the dependent variable, we're going to utilize an independent variable. Now in multiple regression, we have a many-to-one relationship. So we still have one dependent variable, but we can have two or more. In this case, we have three on the screen, but we can have more than that or just two independent variables that are being utilized to explain the variation or predict the value of the dependent variable. So we go from a one-to-one relationship to a many-to-one. Let us look at some considerations. Now having more independent variables complicates things a bit, so we have to have some new things to consider. The first is that adding more independent variables to a multiple regression procedure does not mean the regression will be better or offer better predictions. In fact, doing so can actually make things worse. This is called overfitting. So let's say we conduct a multiple regression procedure and our model explains 60% of the variation in the dependent variable. Well, for some reason we don't like that. So we start adding in more independent variables. Adding more independent variables will explain more of the variation in the dependent variable, but it can open up a whole new set of problems that we definitely want to avoid. The other concept is that the addition of more independent variables creates more relationships amongst them. So not only are the independent variables potentially related to the dependent variable, they are also potentially related to each other. Now when this happens, it is called multicollinearity. The independent variables should be correlated with the dependent variables but not with each other. Now because of multicollinearity and overfitting, there is a fair amount of work before conducting multiple regression analysis. So things like correlations, scatter plots and some simple regressions between the independent variable, each one of them, and the dependent variable must be done just to see how they are related. This is the population regression model. It was assumed that there is a linear relationship between the dependent and independent variables, which is an important assumption in MLR analysis. The population regression line is defined as follows. Here, fxi is the dependent variable, that is the fatigue life of the automotive coil spring, and xi is the ith independent variable. In our application, as you can see, we have two independent variables. First, natural frequency of the vehicle suspension system, and second, vertical vibration of the vehicle, and one dependent variable, that is the fatigue life of the automotive coil spring. Now, we'd like to utilize those two independent variables to make predictions about the dependent variable. The methodology adopted in this study consists of 5 major steps: data acquisition, finite element analysis, simulation of the quarter car model, signal processing, and development and validation of the MLR-based spring durability models. This is the flowchart of the methodology adopted.
In this study, a 1300cc sedan was chosen as the case study vehicle. This car model has a front McPherson strut suspension system. A single-axis accelerometer was attached to the lower control arm of the vehicle at a point close to the hub carrier, whereas a strain gauge was attached to the coil spring. Next, the vehicle was driven across 5 types of roads: highway, rural, residential, hill, and campus, in order to collect the random vibration data. The accelerometer and strain gauge were connected to the data acquisition system, which recorded the signals detected by the sensors, and these signals were transmitted to the laptop computer. Despite the variations in the vehicle speed, realistic vehicle vibrations induced by road excitations were captured, and these data were used for the simulations. The acceleration versus time and microstrain versus time graphs from the study are also shown here.
The automotive coil spring was designed considering the given parameters, and the spring rate was estimated using a simple compression spring equation as shown. For the spring FEA, the applied element size was 2 mm. Rigid body elements were used for the top and bottom of the spring. The degree of freedom of the top rigid body element were constrained, whereas a nodal force of 3000 Newton was applied at the bottom rigid body element. The target stiffness of the automotive coil spring was varied from 14 to 32 Newton per millimeter, with 2 Newton per millimeter increments. The bar diameter of the automotive coil spring was varied in order to obtain the desired spring stiffness. The other geometrical parameters and material properties of the automotive coil spring were fixed because varying these parameters will affect the working space of the vehicle suspension system. Natural frequency of the suspension system should be within a range of 1 to 1.5 Hz in order to ensure optimum ride comfort for the passenger cars. The spring stiffness range for the sensitivity analysis was chosen based on this range of natural frequencies. SAE 5160 carbon steel was chosen as the material for the spring because this material is widely used in automotive coil spring fabrication. The properties can be seen in the table. Linear static analysis was conducted because the fatigue analysis was static and independent of time. The simplest vehicle model used to assess the discomfort due to vibrations is of 2 degrees of freedom and is the quarter car model. Only the vertical motion is considered. The tire is represented by a stiffness, suspension is represented by a spring and damper in parallel, and the vehicle body as mass. The damping coefficient of the model is 15564 Newton second per meter. The front McPherson strut suspension system was modeled using a series of interconnection points where the coordinates of the hard points were set using a multi-body dynamic software, and they can be seen in this table. The mass and moment of inertia in the x, y, and z axes of each component in the vehicle suspension system are presented in the table. Backward differentiation formula is one of the implicit schemes used for numerical integration of ordinary differential equation, where the solution at the current time point is approximated based on the solution computed at the previous time points. This in turn increases the accuracy of the solution. Once the simulation were complete, the force time histories, that is the force transmitted to the automotive coil spring with respect to time, and acceleration time histories were extracted from the solution.
After conducting finite element analysis and quarter car model simulation, the data obtained was analyzed. Acceleration time histories of the sprung mass and force time histories of the unsprung mass from the quarter car model simulation were used to analyze fatigue in the coil spring and vertical ride quality. Acceleration time histories of the sprung mass were weighted according to the procedure outlined in the ISO 2631 1:1997 standard. The force time histories and the finite element analysis results of the automotive coil spring, along with the material properties of the vehicle suspension system like mass and moments of inertia, were used as inputs for the analysis. Further, 3 strain life models were chosen. A strain life model is used to predict how long a product will survive when it is subjected to cyclic loading. 3 strain life models were used because the spring was to be subjected to high cyclic loads, which would result in its plastic deformation and thus a decrease in its fatigue life. The 3 models chosen were Coffin Manson, Morrow, and Smith Watson Topper uniaxial strain life models. These strain life models are suitable for high cycle fatigue analysis. Strain life models have been widely used for fatigue analysis of automotive components such as leaf spring and damper spring towers. The 3 chosen models are defined by the following equations, where eta is the plastic strain, eta f prime is the fatigue ductility coefficient, sigma f prime is the fatigue strength coefficient, b is the fatigue strength exponent, c is the fatigue ductility exponent, sigma mean is mean stress, and sigma max is maximum stress. The rain flow counting method was used for determining the equivalent amplitude and range of the stress as the component was subjected to cyclic loads of variable amplitudes. Rainflow counting is a method to determine the number of fatigue cycles present in a load time history. A fatigue cycle is the loading and unloading of a part. Further, the Palmgren minor use rule was then used to calculate the cumulative fatigue damage given by D. Multiple linear regression was selected to model the relationship between the natural frequencies of the vehicle suspension system, the vertical vibrations of the vehicle, and the fatigue life of the automotive coil spring. As we know, multiple linear regression models a relationship between multiple independent variables and a single dependent variable. Here, the independent variables are the natural frequencies of the car suspension system and the vertical vibrations of the vehicle, and the dependent variable is the fatigue life of the spring. It was assumed that there is a linear relationship between the dependent and the independent variables. The population regression is defined by the given equation where f of xi is the dependent variable and xi is the ith independent variable. The fatigue life values predicted by the Manson, Morrow, and the Smith-Watson-Topper models were compared with those determined from the experiments in order to validate the prediction models. A higher coefficient of determination given by R square indicates that a high percentage of the variability of the dependent variable is explained by the regression model. The crest factor indicates the largest peak in the random time varying signal. The crest factor has a significant effect on the vertical vibrations of the vehicle and also the fatigue life of the automotive coil spring. A high crest factor can result in high fatigue damage, which reduces the fatigue life of the automotive component. It's observed that the highest crest factor is attained for the campus road profile because of the frequent impacts of the bends and curves on the vehicle suspension system.
The datasets comprising the fatigue life values of the automotive coil spring, weight acceleration values of the vehicle, and natural frequencies of the vehicle suspension system were used to establish the MLR-based spring durability models. NCM, NM, and NSWT represent the fatigue life predicted by the Coffin-Manson, Morrow, and Smith-Watson-Topper MLR-based spring durability models, respectively. Omega n is the natural frequency of the vehicle suspension system, and Wa is the weight acceleration, which is the vertical vibration of the vehicle. The response surfaces of the regression models were plotted in order to analyze the data trends. As shown in the figure, the fatigue life, which is the dependent variable, was plotted on the z-axis, whereas the weight acceleration and natural frequency, which were the independent variables, were plotted on the y and x-axes respectively. Following this, the goodness of fit was assessed for each MLR-based spring durability model. The coefficient of determination, which is R square, values were determined in order to assess the goodness of fit of the Coffin-Manson, Morrow, and Smith-Watson-Topper MLR-based spring durability models. A high R square value indicates that a high percentage of the variability of the dependent variable is explained by the regression model. The R-square value for the Coffin-Manson MLR-based model is found to be 83% with a mean square error of 0.5282. The R-square value and MSE are slightly higher for the Morrow MLR-based model with a value of 88% and 0.5855 respectively. The R-square value of the Smith-Watson-Topper MLR-based model is the same as that for the Coffin-Manson MLR-based model, which is 83%. However, the MSE 0.7056 is highest among the three models. Overall, the R-square values are more than 80%, indicating that the models are reliable to predict the fatigue life of automotive coil springs. Regression models with an R-square value of more than 0.9 are classified as very good, whereas those with an R-square value of more than 0.8 are classified as good. However, it shall be noted that there are no hard and fast rules for the R-square value.
The normal predicted probability plots of the standardized residuals were plotted for the three MLR-based spring durability models. It can be seen that the data points lie within proximity of the normality line, that is the diagonal line in the normal PP plots, implying that the distribution of the dependent variable is normal for each independent variable. This justifies the normality assumption for the MLR-based spring durability models. Analysis of variance was performed to determine the dependency of the fatigue life of automotive coil spring on the weighted acceleration and natural frequency of the vehicle suspension system. The F ratio was used to test whether the overall regression model fits well with the data. Even though the ANOVA results reveal the significance of the MLR-based spring durability models, they do not provide the significance of the independent variables. If p-values of the predictor variables obtained from the t-test are lower than 0.05, the predictor variables are considered to be significant. The t-values are highest for the constant alpha, followed by the weighted acceleration, and the least of all, the natural frequency. Nevertheless, all of the predictor variables are significant because the p-values of these variables are less than 0.05.
Histograms of the standardized residuals were plotted for all three models to examine the normality of the error terms. Residual is defined as a difference between the observed and predicted values, and the residuals help to identify if there are any outliers in the regression model. From the plotted histograms, it can be observed that standardized residuals approximately follow a normal distribution and there are no outliers detected.
It is important to examine the distribution of the standardized residuals using scatter plots to ensure that the MLR-based spring durability models fulfill the homoscedasticity assumption. It is the assumption that the variation in the residuals or amount of error in the model is similar at each point across the model. In other words, the spread of the residuals should be fairly constant at each point of the predictor variables or across the linear model. This can be done by plotting the predicted values on the x-axis and the standardized residuals on the y-axis for the three models. The distribution of residuals in the scatter plot is almost symmetric, and the residuals tend to cluster towards the middle of the scatter plot. It can be observed that there are no distinct patterns in any of the scatter plots, and the standardized residuals appear random, indicating that the MLR-based spring durability models fulfill the homoscedasticity assumption.
In this study, the Mahalanobis distance values were also determined to check the existence of outliers in the independent variables based on the chi-square distribution. The Mahalanobis distance refers to the distance between each point from the mean value. The chi-square test with 2 degrees of freedom was chosen for analysis because all of the MLR-based spring durability models consist of 2 independent variables. If none of the Mahalanobis distance values are greater than or equal to the critical chi-square value, which is 13.82, for 2 degrees of freedom at a significance level of 0.001, this means that there are no outliers in the MLR-based spring durability models. The figures here show the critical chi-square values of the data points for all three MLR-based spring durability models. It can be seen that none of the critical chi-square values are less than a significance level of 0.001, indicating that there are no outliers in the models. The Coffin-Manson model provides good estimates of the fatigue life when the main stress effects are neglected from the analysis. Otherwise, the Coffin-Manson model gives conservative predictions. In this regard, the Morrow and Smith-Watson-Topper models give better predictions of the fatigue life of automotive components when mean stresses are taken into consideration. For steels, the Morrow strain life model gives accurate predictions of fatigue life, but the results are non-conservative when other alloys are used. The Smith-Watson-Topper strain life model gives accurate predictions of the fatigue life for all types of alloys. So once the goodness of fit, linearity and normality of the MLR-based spring durability models had been examined, the models were validated by comparing the fatigue life values predicted by the models with those predicted from strain measurements as shown in the figure. It can be observed that the fatigue life values predicted by the Coffin-Manson MLR-based model show good agreement with the experimental fatigue life values, with an R-square value of 0.9643. The root mean square error, which is RMSE, is a statistical parameter that indicates the deviation between the predicted and experimental values. It's found to be 0.4857 for the Coffin-Manson MLR-based model. The R-square value and RMSE for the Morrow MLR-based model are found to be 0.9275 and 0.6401 respectively. The R-square value and RMSE for the Smith-Watson-Topper MLR-based model are determined to be 0.9806 and 0.624 respectively. In this study indicated that 98.06% of the variability in the fatigue life is described by this model. Even though the Smith-Watson-Topper MLR-based model has higher RMSE, the correlation between the predicted and experimental values is excellent. Overall, the R-square values are more than 0.9 for all of the MLR-based spring durability models, which indicate the reliability of the models in predicting the fatigue life of the automotive coil spring.
So, in this study, multiple linear regression based spring durability models were developed based on the Coffin Manson, Morrow, and Smith Watson Topper's train life models to predict the fatigue life of automotive coil spring and vehicle ride quality. The R square values obtained from the experiment and from the multiple linear regression based spring models are listed, and they indicate that there is a very good agreement between the predicted and experimented fatigue life values. The results indicate that the MLR based spring durability models are able to predict the fatigue life of automotive coil springs with reasonable accuracy. It is believed that these models will significantly simplify the design and development process of vehicle suspension systems by providing reliable predictions of the fatigue life of automotive coil springs based on the vertical vibrations of the vehicle according to the ISO standard.